is Hello everyone. Today is about hoverboard motherboard hack. I will make one video, complete video, how to hack and how to steer the hoverboard motherboard. I will write full this hardware configuration with STM32 CubeMX. Then I will write the code in CubeIDE. So it is a new program will generate. Just go new project. I am starting one by one each and everything. You will enjoy. Also you can learn the hoverboard and you can learn the microcontroller, how to coding. So be with me. So our microcontroller is STM32 F103 and in the motherboard it is RCT6. So we'll go to the RC. Here you can see RC available, and here two type it is showing. If you choose this one, you can see it will display like this. So we will choose the other one. So always you choose the first one, LQFP64. Double click and this clear pinout view you can see here. So here you can see the picture of the hoverboard motherboard. So I will assign these all pins. This is for the here debugging header, okay, and here which pins are connected you can see here. This is debugging header here. So I will put here 4 pins for debugging. So I will use PA13, PA14 and 3.3 volt and ground. Then I will go first the timer 8, then left porter PC678, PA7, PB0, PB1 I will choose. Same like right porters, these pins I will select. And then for the Hall sensors and the motor current charger pin and for the ADC pin and for controlling the speed and direction, I will choose one by one all the pins. So here our STM32 F103 RCT6, actually here they show X 64 pins. It start from here, see VBAT start here and end here. This is pin 64, then 1 to 16 here, then like this. There is 64 pins. First we'll go to the pin out and configuration, then system core. In system core go to the sys and choose here serial wire, and time based source is system take. Okay, when I choose the serial wire, you can see here PA13 and PA14 is configured here as a hardware. These are STM32 dedicated SWT pins, and they are not general purpose like this. Here if you choose another GPIO output or input, they are not general purpose by default. PA13 is SW clock, serial wire clock. It carries the timing clock from the ST-Link programmer to the MCU. And PA14 here you can see is SWDIO serial wire data input output bidirectional data line for command, code, upload and debug. And you know why it is required. This is required for upload program to your MCU without PA13-14 connected correctly. Node wise found, if you connect it, if it is not configured, could not verify the ST device, CubeIDE, CubeMX, programmer cannot talk to the MCU. This is our MCU. If it is not properly configured, then you cannot talk with this one. Talking means they are using for debugging and live control. So they let you set breakpoints, watch, variable, test, motor control live. So also you can use in the STM motor pilot for tuning. By factory default, you cannot change PA32 and have a permanent function SWD. They are not regular GPIO. After reset, SWD mode is automatically enabled if it is original Nucleo board. So that's why we need this one. It is connected to, if it is not by mistake we change and not connected, what you will get connected but still no device found, work sometime, failure other time, PA13 show low constantly. So that's why it is important you in the CubeMX for the debugging process and proper work you set the as a serial wire, and normally we'll go to 950 kilohertz, best for custom boards. So our hoverboard is custom board. Here you can see this is our hoverboard and this is the custom board. You can see this is our MCU, and this is 7805, and this one M1117 voltage regulators. This is converting voltage from 36 to 15 volt, and this one 5 here we are getting 5 volt, this one 5 volt to 3.3 volt for MCU. This is the other regulators for the power section, and here back side you can see here each side 6 MOSFET here, 6 MOSFET here. This is for the BLDC motor, and this is the header where we connect the pin for the debugging, and this is motor wires, left and right motor, and this is our here power supply, first to negative then positive, and this is the on off switch, and here you can see the shunt resistors, capacitor, and other things also there. Okay, one by one, so we'll go through. This is the clear picture of the MCU STM32 F103 C8T6 also I have, and this one RCT6, this is 64 pins, and which I am using here for the coding. And there is another board that is having GD32, and that connection is like this for the serial pins for the debugging. And this is the ST-Link V2 which we are using for the debugging. You see here we connect the ground and the clock and the data pin, and positive supply we give here in the power. Even if you give here, that also sometime works. If it is not working, then you can give the separate power supply through the battery or through the charger, any pin you can apply. Okay, now you can see clearly this is debugging header, and here we can like this pin and we can solder it. Here you can see this is board is GD32, and the pins almost same identical 64 pin, and you can see here timer 8 and timer 1, and the pin numbers 6 pins selected here, 6 here, and also as you can see GT32 F103 C8T6, and same PA2 PA3 PB1011, only little difference, sometimes this side this side, but almost matching, and pin number identical, same matching for GT. Here you can see these are the pins which is configured for our hoverboard, and I write here each pin, and also I trace the lines on the hoverboard. Actual video the here back side of this one, and here you can see now total how many. This here you can see this is the header which we solder for the flashing. This is the back side of the hoverboard, and you can see here 6 MOSFET left motor, 6 MOSFET right motor, and this is our motor. For that, so you we can are doing see I coding here the this one magnet. After that we'll go here timer section, same pinout configuration, and here timer. First I will choose the timer 8, here core clock source, internal clock, and channel 1 BL and 1 PWM, same like PWM generation, channel 1, channel 2, channel 2N, and same like here PWM, channel 3, channel 3N. Okay, you know why this? We configure total 6 pins. So this is timer 8. You click here, timer 8 channel 1, timer 8 channel 2, timer 8 channel 3, same here, timer 8 channel 1N, 2N, and timer 8 channel 3N. These timers are not optional, they are the heart of the motor control. Without timer you cannot drive the motor at all. These are general PWM signal. BLDC motor needs 6 PWM signal, 3 high side and 3 low side. So when I rename it, then you can see it. And PWM is pulse width modulation, is rapidly turn MOSFET on and off to control the voltage and speed. Only timers can provide accurate PWM at 16 to 20 kilohertz, silent no hum. So each PWM channel one timer, 6 outputs, timers with 6 channels. So like that we choose here. So what it is doing, it is measured rotor position from the Hall sensor. We have 3 Hall sensor. I will show you in the motor. Here you can see this strip. These are our Hall sensors here, and it is connecting to the motherboard here. This is the single motherboard, single motor. This is the dual motor, and this is our ST-Link, and this is another type of motor controller. Here coding not required. So we have everything. Uh, 3 Hall sensor tell exactly when to switch phases. That is called commutation. Hall signal change 6 timers per full motor rotation. Timer input capture mode, continuous count time between Hall edge, calculate RPM, speed, direction. So precise timekeeping and synchronizing motor control loop must run at fixed interval. Timers trigger interrupts, code runs instantly. So FOC 6-step math on time. So in this code we'll use timer 4, timer 8, timer 1, timer 2, timer 3. All will use some for the Hall sensor, some for the right motor and left motor. So what is the job of timer? PWM generation 16 to 20 kilohertz, Hall RPM measurement, precise control, loop timing, dead time protection. So this is the purpose of the timer. So simply in one sentence, timers, PWM generation plus position measurement plus timing heartbeat. Without timers, no motor control is possible. Here you see we use here PWM generation, channel 1, channel 1, and like this channel 2. So what is PWM? PWM is rapid on off switching, fast enough for 16,000 to 20,000 times per second. This much fast for motor C average voltage. Duty cycle is 0% of time signal is high. Okay, if duty cycle is 0, this means motor is off. If duty cycle 50%, motor gets half voltage, so half speed. If duty cycle is 100%, motor full on, full speed. And why PWM is required? You cannot control the speed just turning the voltage up and down. BLDC need precise voltage control and phase timing. Only timer PWM can give fixed frequency, accurate duty cycle, smooth speed, and torque, dead time protection, and standard. I already told you. So we use some values. Prescaler is 0. Later on we'll set here prescaler, and okay. Then period here we'll set to ARR to 4499. So auto reload will select here 4499. This means 72 megahertz. If we divide by 4500, so it will give us 16 hertz or 16 kilohertz. And this means 0 to 4499. This is its resolution, very smooth control. And this is we choose for phase A, B, C. So we'll rename it. Just right click, enter user label, and this is our label here. Left motor W high, then same for other one, because there is 3 phases. So this we rename as per our requirement. Same for these pins. We'll change the label. See, left motor U, and here is our V, and here W. So this means phase A, B, C, U, V, W. You can rename it. And this is on timer 8, channel 1N, left motor, low side. And same like here, this UVW or phase A, B, C, and this is for the high side. Same like that. Then we'll select for the right motor. Here again, same clock source, internal clock, channel, PWM generation, channel 1 N, and you can see here the channel 1 timer 8, timer 1 channel 1 here it is configured, and channel 1 N. Same we do for the channel 2N. Same for the PWM generation, channel 3N. Again we configured another 6 pins for the right motor. Now we rename it. So here it is timer 1, channel 1, 2, 3. So we right click, enter user label, tool V. So this is right motor, UVW 3 phases, or ABC, whatever you want. This is high side. I will rename it all the pins. Actually this is a long video. It's taking more time because I am doing practically with you. You can watch, and same time you can configure the pins and you can rename the pins. Same the enable pin, we can rename it. So another 6 pins we enabled for this 2 timers. So total 12 pins enabled for timer 1 and timer 8 for the 2 BLDC motors. After that I will use the Hall sensors pins. So 3 Hall sensor inside the motor. What it is telling, it is telling the exact where the rotor position. It is the brain of the motor. Also we can use it as a GPIO input. So I will use this one also, GPIO input, and for the left and right both I will choose these pins, and also I will rename. So we rename it left UVW or ABC, whatever you want. Same here, right click and we give the label. Okay, this is for the left Hall and this is for the right Hall sensors. And after connecting this one, you can check it in the uh, GPIO. Here in the pinout and configuration, go to GPIO. You can see here 6 pins are selected, also user label also there, which we give the label. It is also coming here user label, same like timer 8. If you go here GPIO, and you can see here 6 pins also selected here, and the timer 8 also 6 pins are selected here. Okay, now I will discuss about this one. This 3 Hall sensor inside the motor tell exactly where the rotor is positioned. As rotor spin, a magnet inside present, so it passes through the sensor. So each output shows high or low. So 3 signals equal to 6 unique combination, each one of 6 motor rotor position. So 3 signals, 6 unique combination, each equal to one of the 6 rotor position. So controller reads the Hall pattern, know exactly when to switch phases, called it is called 6-step commutations. So without Hall sensor, motor does not know its position, cannot start or jerky start. It is also we can use for measuring the speed. If you need some more information, why 3 Hall per motor, this is for now 6 position, exactly when to switch the phases on and off. And time when timer 4 and timer 3, so these are internally connected. They have input capture, read position, and plus speed in hardware. So no CPU lag. And why we use PB567 and PC10 11 12. These pin are alternative function of timer 4 and timer 3 for hardware connection, which we use inside. If we disconnect, what will happen? Motor cannot find the position and won't start, vibrate, stall position. Uh, uh, can we change these pins only if that pin has the same timer uh, channel alternate function? So they are correct alternate function pins. So finally, PWM timers make motor turns. Hall timers tell PWM exactly when to turn. Both required, cannot work without or either. After that pinout configuration, go to the RCC. Here high speed clock, HSC, crystal ceramic resonator. When you select, you can see here these 2 pins again configured. And if you see, this is RCC, oscillator in and out, and this is PD0 and PD1. uh, RCC means clock configuration, crystal versus ceramic. What is the clock? Why MCU cannot run without it? So uh, clock means crystal clock, uh, high speed clock. So clock is the heartbeat of the MCU. This is MCU and this is the clock, and this is the heartbeat. So MCU cannot run without it. Every instruction, every PWM signal, every timer counter all run in synchronize with the clock. Okay, so if no clock, so this means MCU is dead. Unstable clock, motor jerky, drift, UART fail, PWM wrong. So that's why we are using. So in the pin clock configuration, you can see here HSI, HSE, PLL. This HSI means internal clock, and that is here. And HSC means external clock, PLL is multiplier, and here you can see the frequency is 4 megahertz. And after that this in detail I will discuss again. And this one so crystal clock versus ceramic resonator. So crystal is recommended for this board. This accuracy is perfect, and stability, it is do not drift with the temperature or voltage. But if you use the ceramic resonator, see, accuracy is less, and when the temperature is high it will drift. And HSI internal clock actually we never use for the motor. Always we are using the external. HSI means this drift hundreds of kilohertz. Uh, so the timer PWM frequency change, motor harm or overheat. So UART control fail. So that's why in motor control rule must be a HSE external clock. And this is we use 8 megahertz quartz crystal HSE, that is good. And the pin number, PD0 and PD1 we use. And after the HSE PLL 8, and we will use here PLL clock, and it becomes 16 sys clock. And AHB1 prescaler 1, and its H clock is 16. This means equal to 72 megahertz. And here we will not change anything. So here 72, but here it become again 36 megahertz. So it will divide by 2. No, you can see it is matching here. APB 1 timer clock 16 megahertz, B timer also 16. So this is matching for us here. Here you can see here PLL is 8 and we multiply by 9, so total 72 megahertz. And here you can see everything is equal to 72 megahertz. So this one is the setting. All timers, PWM, Hall, UART, and work perfectly together with this one. And 8 megahertz crystal, PLL 9, 72 megahertz, APB1, APB2, all are happy. Sometime is not correct, then this resolve clock issue will come, and you can click and you can resolve the issue. This system itself, it will resolve the issue and match the then after that PA12 I will put here input. And this is our user label. We'll put here the charger pin, and then PP2 here will select as a output. So we'll label it as a LED pin. And PA5 also we use as a input, and we rename it. This we will use for the off pin. And PA4, this will select as a output, and we label it as a buzzer pin. So we are configuring each and everything. And PA2, okay, after that go to analog, ADC1 IN0. If you select, then you can see here PA0. This is wake up pin. This is enabled here. Then IN2, and with IN2 you can see ADC2, ADC1, IN2, PA2 is configured. Then we'll select here IN11, IN12, and I will rename it. then you can see what is the function of these pins. Then we'll go for the ATC2. Here we'll select IN10 and you can see PC0 is enabled here with IN10. Then we can select IN13. When I enable and when I rename, then I will tell you each and every pin. Then IN15. So this is also enabled here. So these all pins are enabled. Now we'll discuss about the function. So first is ADC1 IN10 PC0. I will use it. I will label it left DC current. The function is purpose is PC0 left DC current. It is measure total DC current of the left motor on the DC bus. Measure current flowing from the battery inverter to the motor. This pin is used for that one, and it is used for the current limitation, overcurrent protection, torque control. So in the pinout configuration already you see PC0, it is in ADC 1 IN10. Here I can show you here this one, and here you can see here ADC1 IN10. Even though this one also working on ADC2 IN10 also. If you this one, this is on ADC1 IN10, ADC2 IN10 also it is working, so we can select any one. So how it is working from the battery voltage going to shunt resistors, that is 3.5 mega ohm to 7 mega ohm, then inverter and to the motor, and if any voltage drop proportional to the current, uh, output amperes amplifies signal. So PC0 ADC1 IN10 read the voltage, and there is shunt resistors on the hoverboard. I will show you, and you can see here this one, two shunt resistors on the left side and to the right side. That R007 means uh, so this is R007. This means equal to 0.07 ohm, or 7 millions. You can do R is like this decimal point. R007 means 0.007 ohm, and this purpose is it measure the current voltage drop. 1 is equal to resistance and standard hoverboard value. There is two R007 in the parallel, so it is on two faces. If you know the Ohm law, so then you can read this one how it is working. So I'm not going that much detail. So only simple I can tell you this R007 means 7 milliohm for the shunt resistors, and two in parallel, so it will give 3.5 milliohm. Single R007 get hot at 30 ampere. This is other settings. So it is very simple. This means two shunt. It is measuring two phases, and from two phases it is calculated the third phase. This is the rule for that one, means A plus B plus C equal to 0. So therefore then 1C equal to A plus B. So like that it is measuring the voltage. That is math calculation. So only the purpose is for using two shunt resistors is best balance cost and performance used on all STM32 motors, workbench, hoverboards. So how it is working in current phase A, read via PA0 ADC1 IN0, and 1B read current phase B via PC3 ADC1 IN13, which is our setting here. So here it is connecting. Same like that, the other one also we can change the label here, PC1, and I will put here the label. This is right DC current, and this one ADC12 also I will use here. This is a battery DC link. So this is battery DC link, very easy, means it is measure the DC link voltage, measure battery voltage, DC bus voltage, and measure in the main supply voltage that power the inverter and motor. It is used for over voltage protection, under voltage warning, and FOC, feed forward speed calculation, and this is the purpose only for this one. If I go more details, means if battery, it is for the battery voltage protection. If voltage is 42, it stop motor, prevent destruction. If voltage is lower and 30 volt it is measuring, then power is reduced, so battery will discharge, deep discharge, so it is protection for the battery. And FOC, feed forward, PWM duty, automatically it is adjusting by measuring the voltage, and it is also telling the state of charge. It knows the battery percentage, how much battery is charged or already used, discharge. After that, this will use here as left phase B current. So this PC3 function we are using for left phase B current, and this is on, it is available on ATC1 IN 0, ATC2 IN 0, ATC3 IN 0 also it is available. So this is the role of this one in the two shunt system.